right? I should okay. We have seen how to prove that the recursive method is correct without going through the trace of the algorithm. That is not easy. Now we will talk about the analysis of recursive algorithms. This is the general plan for analyzing efficiency of recursive algorithms. With all the algorithms as other iterative algorithms, we have to decide on the parameter indicating the input size. So we have to decide the what is the running time. Let's say we have to write Tn for the running time. What is this n? N is, for example, for these, n is the size of the string, right? The number of elements in the string, number of characters in the string in this case. So first we have to identify how we are going to measure the input size or problem size. So that is the first step in algorithm analysis, in analyzing recursive algorithms as well. Then we calculate number of operations executed at each recursive call. Here we do not consider recursive methods, recursive calls actually, and we try to come up with number of operations executed for each recursive call, and using that we set up a recurrence relation. What's the recurrence relation? Probably you have seen recurrence relations in discrete math course, so you all know the recurrence relation. Recurrence relation are the functions that are defined in terms of themselves. For example, if fn, a function, is defined by some fn minus 2 plus 7, for example, fn is defined by using the same function, then we call this kind of relations as recurrence relation. Okay, this is a recurrence relation. So we try to set up a recurrence relation. Since we have recursive calls, for example, here in this example, if I say that Tn is the running time for this algorithm, of course, for this recursive call, the running time is in terms of t as well. If the string has size n, what is the size of the string, which is n minus 1. So for a string of size n minus 1, this function call will take a t n minus 1 time, right? Plus the operations performed during this recursive call, excluding this recursive method call, right? So how many operations are there? For example, checking whether a string is null or string equals to an empty string is constant time, right? Or this addition will take constant time. So all these are constant time operations. But what about this substring method? How long does it take? How long does it take to get a substring starting from the index 1? What? I couldn't get it. Why is it linear time?
Because it's checking all members of the string.
No, I'm just saying that I'm talking about taking a substring just once. I have a string and I'm creating a substring of that string in this not recursive call. I'm not talking about recursive call in this parameter. I have to calculate a substring starting the first position, right? How long does it take?
Constant time.
Constant time? Why? I have a string, right? In some memory location. And when I make this call to substring method, what happens?
Kaydırma yapmıyor mu hocam? O yüzden o n değil mi?
There is no shifting or anything. We do not insert anything. We do not delete anything. Actually, the strings are immutable in Java, right? If this is a string located in this in the memory, we cannot modify the string. It is immutable.
It creates a new string and copies all the elements starting with.
That's right. Because it is immutable, it creates a new string in another memory location. For this string, we have n characters. For this new string, we will have n minus 1 characters, and everything here is copied in this one. Since in Java, the strings are immutable, that needs to be done. And it is not constant time operation because of this operation. Is it clear? We have to copy n minus 1 elements from one location to another to perform this substring operation. It looks like constant time operation, but it is not. You have to be careful about it. You have to know about Java to say the running time of this operation. And that's why you have to be careful about using substring, since it is not constant time operation. So n minus 1 elements are copied. And 1 is incremented and return is over here. So theta n operations are performed other than this recursive call, right? Is it clear? What about this one? Again, the running time is Tn. Of course, we make a recursive call here, which will take Tn minus 1 time to print out n minus 1 elements in this substring, right? Plus, forming this substring will take linear time, and printing a character is constant time. Checking whether string is empty or not is constant time, etc. So we will have another theta n time to perform these operations. So, in a sense, let me go through here. Here we perform theta n operations. Here we perform theta n minus 1 operations. Here we perform theta n minus 2, etc. At the end, we perform theta 1 operation to check whether the string is null and it is, or the string is equal to empty string or not, which is a constant time operation, right? So the overall running time is the addition of these. Right? And addition of 1 and n minus 1 and minus 2 and until 1. So the running time is I equals 1 to n, this one, which is theta n squared. The running time is theta n squared. Why? Because of this substring method, which takes linear time. And actually, in analysis, let me go to this position again. We set up a recurrence relation. In this recurrence relation, we say that Tn minus 1 plus theta n, if the size is large, since we perform recursive call which takes Tn minus 1 time. But we should consider the initial condition or base case as well. We have to write an initial condition when n is small. For example, if n is 0, we take constant time, right? This is the whole recurrence relation. It has two terms. One of them is for the general case, where the recursive call is performed. The other one is for the base case. This is for the base case. This is for the recursive case. Okay, so in here, when we find the length of a string, saying this one is not enough, you should also consider this base case and say that if the size is 0, it is constant time operation. For size is 0, it is usually constant time operation, but it is still needs to be specified, since sometimes the base case is not constant time. Okay, the whole thing gives the recurrence relation. Yes.
What would be if the substring is constant time?
Substring is constant time. You mean the string? Calculating substring is constant time, right? If this operation is constant time, you mean, right?
Yes.
If this operation is constant time, this operation is constant time as well. Controlling whether the string is empty or not is constant time. So this makes constant time, right? So if it was like that, everything here will be constant time, and the result will be addition of ones here, and it will make theta n, right? Is it clear? But it is not in Java.
Okay, thank you, sir.
Okay. So this is the recurrence relation for this method. How did we get it? First of all, we find the input size, which is n. N is the parameter of this Tn, as you see, right? The running time will depend on n. Then we try to find the recursive call and the size of the recursive call's parameter. If the size is n, for the recursive call, the size is n minus 1, right? So the running time of this recursive call, actually I shouldn't put like that, this recursive call is Tn minus 1, right? So the overall running time is the recursive call, finding the substring, adding 1, checking whether string is null, and checking whether this string equals empty string, right? This is constant time. This is constant time. This is constant time. But this is linear time. So addition of all makes Tn, right? Tn is Tn minus 1 plus linear time, constant time, constant time, constant time. So all of them makes linear time, right? We didn't consider this a return, right? Why? Because it is the base case. If it is if the string is null, we perform this operation, and return 0. And running time will be constant time, constant time, constant time. The total is constant time, and it is in here, right? If the size is 0, the running time is constant time. Is it clear? So how we form this recurrence relation? Any questions so far?
Sir, what would be if there are two length function?
If
the
there are
function.
more than one recursive calls, right? We are going to come to that point later on, but if there are two recursive calls like plus length, like str substring from true, for example, right? We are talking about this one, right? If there are two calls like this, we are going to check what is the size here, n minus 1. So this call will take Tn minus 1 time, right? What is the size here? N minus 2, for example. What is the running time of this one? Tn minus 2. Since actually this call will run this one, right? With different size string, right? And the string size is n minus 1 or n minus 2 in different cases. So this recursive call will take Tn minus 1 time, and this recursive call will take Tn minus 2 time. Is it clear? We are going to see some examples of this later on. For the time being, this is the running time, the recurrence relation for this one. Let's keep it. What about the recurrence relation for this one? Again, same, right? For t is equal to t0 means for the base case, the running time of this operation is constant time. And for the general case, n greater than 0, this is when n is equal to 0. You can write it like this as well. Okay, the same thing. if n is greater than 0, we perform this check anyway, right? We print out something in constant time, constant time, constant time. We calculate this substring, which is linear time, and print characters for this substring, which has n minus 1 characters, right? Printing these characters will take tn minus 1 time, and the substring calculation is linear time, so we have linear time here. Same thing for this one, so I'm not going to go into detail. Is it clear? Okay, so what we do is we try to set up a recurrence relation for number of operations executed, but sometimes the number of operations executed at each recursive call is not, we cannot write it in theta notation. It varies for different input size, for different input of same size. In that case, we have to analyze worst case, average case, and best case runtime efficiencies. So in that case, we may talk about the worst case running time and a recurrence relation for the worst case running time, and we can talk about best case running time and a recurrence relation for the best case running time, probably. Is it clear? So it may not be that easy to write this function, and in that case we have to go through worst case and best case usually, and average case sometimes. Okay, but what we get is a recurrence relation with appropriate initial condition. Initial condition should not be forgotten. You should put an initial condition as well. But this is a recurrence relation. This is not something like Tn is theta n square kind of thing. To get this kind of closed form solution from the recurrence relation is to solve the recurrence relation. Next thing to do is to solve the recurrence relation to get the growth rate of the solution or the value of the function, as in here. Okay, how are we going to solve the recurrence relation? For example, here we kind of solve the recurrence relation since we know that theta n time is spent for this first recursive call, excluding, of course, this recursive call, right? This recursive call will be handled here, and the running time of that recursive call is in here. And in that one, we have another recursive call here, and the running time is in here, right? And we should add them up to get the overall running time, which is theta n squared. This is one way to do it. Another way to do it is we know that Tn is Tn minus 1 plus theta n, right? What about Tn minus 1? We know that Tn minus 1 is Tn minus 2 plus theta n minus 1, right? So in another way, saying Tn is Tn minus 2 plus Tn minus 1 plus theta n. And this is when you open up Tn minus 2, it is Tn minus 3 plus Tn theta n minus 2 plus theta n minus 1 plus theta n. But when you add these up, you have to be careful. It continues like that, right? Until t0 plus theta 1 plus theta 2 plus theta n minus 1 plus theta n. And in that case, this is constant time, right? And the total of these is theta n squared. This is substitution method. To solve a recurrence relation. We substitute Tn minus 1 and Tn minus 2, then Tn minus 3, etc. And try to reach T0, which is the base case, and try to find a recurrence relation solution. Okay? Actually, what is theta n minus 1 plus theta n? We cannot easily add two asymptotic notations, right? There is no arithmetic between asymptotic notations. We cannot perform arithmetic between asymptotic notations, actually. But this is like a function depends on n, and this is a function depends on n minus 1. And we perform arithmetic on them. So you should be careful in doing arithmetic in these. Doing arithmetic on asymptotic notations is not easy. Yes.
Sir, can a recursive function be n cube n to the fourth power and so on and so forth?
Yes, of course it can.
So how do we know it's not n squared and n cubed?
Actually, you should check the number of operations at each recursive call. Here we said linear. It can be more, of course. If we have, for example, if we have a for loop here, a nested for loop that makes the running time theta n squared probably. Okay. And
Okay.
if this were theta n squared, then the overall running time will be theta n cube.
All right.
Okay.
Thank you.
Yeah, so you should be analyzing what is left other than this recursive call and put the running time in here, of course. Right?
And what if T0 was something else other than constant time? Would it make a difference?
Yes, of course. For example, in here, for example, here we have a T0 term, right? If T0 is theta n cube, then it is theta n cube plus theta 1, theta 2, theta n minus 1, etc. And it will be theta n cube then, right? Of course, it makes difference. If T0 is, we say that it is constant time, that makes n squared. If it is linear time, it's still n squared. If it is quadratic time, still n squared, but it is more than quadratic, then the overall running time will not be quadratic time anymore. So it makes difference. But usually, when you come to base case, the base case problem is usually a very small problem, and it can usually be solved in constant time.
Okay, thank you.
Okay, these are simple examples. Let's go over a little more. These are what you know from other courses, probably, how to calculate factorial powers and greatest common divisor for using recurrence relation or recursive methods. We can define factorial of n recursively, as in here. If you can define something recursively, you can write a recursive method based on this recursive definition easily. So to be able to calculate n factorial means this recursion means we need to calculate the n minus 1 factorial first, and multiplying the result with n will give us n factorial. So the recursive method call is very apparent here. We have to perform this operation recursively, right? So if the definition of the calculation is recursive, writing this recursive algorithm is very simple. And as you see here, if n is 0, the result is 1. If n is equal to 0, n factorial is 1. Otherwise, if n is larger, greater than 0, we have to calculate n minus 1 factorial recursively and multiply with n. We have to calculate n minus 1 factorial and multiply with n to find n factorial, right? And we can write the algorithm like, since these are n factorial, we just return, right? And this can be calculated by recursive call, as in here. We calculate the factorial of n minus 1, multiply with n, and return to calculate n factorial. Of course, you can look at these nested calls, one after all the calls of the factorial method for different values, but it is not easy to trace these calls. But it is easy to validate this algorithm if n is equal to 0, whether it is correct or not. Yes, it is correct. N minus from n to n minus 1, n minus 1 to n minus 2, etc. It proceeds through base case. That is correct. And if factorial of n minus 1 is correctly calculated, factorial of n is this one? Yes, it is. So we have verified the algorithm is correction, that this algorithm is correct, right? So without going on this details on this trace, since this trace only validate that factorial of 4 is calculated correctly, we cannot say that factorial of 20 is calculated correctly by this algorithm. But by verifying for the base case and for the general case, etc., we can make sure that this algorithm calculates the factorial for all the cases. Okay. But if you call the factorial method with negative argument, if the argument is negative, it will never be 0. And because of that, the algorithm will go on and on. It will not stop. Make sure of it. You can do 2 things. You can assume that you can check whether it is negative or not, and you can throw an exception, illegal argument exception probably in the algorithm. So having negative value as an argument is another base case which throws an exception actually. Otherwise, if you do not do it, the program will not terminate, and it will eventually throw an exception because the stack is overflowed. Stack is full, right? So you have to make sure that stopping case is always reached in the algorithm. Here, for negative values, the stopping case of n equal to 0 is not reached, so you should be careful about it. So what is the running time? For the running time, you can talk about the running time Tn. N is this value, right? Or you can talk about the number of multiplications that is performed in this algorithm. Since this multiplication is the basic operation that is performed in this algorithm. And this multiplication determines the running times, since the number of times other operations are performed is not larger than the number of multiplications. So the number of multiplications determines the running time. So you can look at the number of multiplications, which is the basic operation in this algorithm. And the number of multiplications is what? Again, we should form a recurrence relation. For this factorial of n, we have mn number of multiplications. What about this factorial method for n minus 1? How many multiplications are performed? Here we perform mn minus 1 multiplications, right? And we have one more multiplication here. So the number of multiplications will be mn minus 1 plus 1 for this multiplication, plus 1. Having this recurrence relation will not be enough. If n is equal to 0, m0 is what? How many multiplications are performed if n is equal to 0? There are no multiplications here, right? So it will be 0. So we have to solve this recurrence relation. How can we solve this recurrence relation? Again, let me find a proper place. mn is equal to mn minus 1 plus 1, right? What is mn minus 1? Which is mn minus 2 plus 1 plus 1, right? This plus 1 is here. This plus 1 is in mn minus 1, right? It comes from mn minus 1. So it is minus 2 plus 2. And what is mn minus 2? It is mn minus 3 plus 1 plus 2 makes 3, right? And if you continue like this, mn is equal to mn minus k for some k plus k, right? In general. And if you make n equals to k, then mn is equal to, this is for this one, m0 plus n, right? What is m0? We know that m0 is 0. Then mn is n. This is the number of multiplications for this algorithm. So when we solve this, we know that mn is n. Means the number of multiplications in this algorithm is n to calculate the factorial of n. And what is the running time? We perform this many multiplications and this many subtraction probably, this many control whether n is equal to 0 or not, right? And the total running time will be theta n. As you see, we can say the number of multiplications exactly as a function, but it is not easy to say the running time exactly, since these recursive calls require forming an activation record, pushing it on stack, and returning from the factorial function requires popping the stack and changing the program counter, etc. So it has a lots of things to be done, and we do not know how many operations are there exactly. So here the asymptotic notation hides some constant here, and we don't know that constant, but calling a function and returning from a function will take constant time. So we we do not go into details of these operations and use asymptotic notation not to consider the details, but consider the algorithm only, right? The running time is theta. As you see, the running time can be expressed as asymptotic notation, while the number of multiplication can be expressed exactly as a function. You have to be careful about it. Is it clear? Okay. Again, to calculate x to the n, you all know x to the n can be recursively defined as x times x to the n minus 1. And by using this recursive definition, we can write this recursive method. So what is the parameter that the running time of this algorithm depends on? Does it depend on the value of x? Does it depend on value of n? Or does it depend on anything else? The answer is simple, right? The running time will not depend on x, since we multiply x several times, but the number of times the multiplication will be performed doesn't depend on x. It depends on n. So again, the running time of this algorithm will be expressed in terms of n, not in terms of x. And the size of this recursive call is n minus 1. So the running time of this recursive call will be tn minus 1. And other than that, we have a multiplication, a constant check, equal to check, or and everything is constant time. So it will be Tn minus 1 plus constant time, right? And we know that T0 is constant time, returning 1, right? So we know how to solve this recurrence relation, and we know that Tn is theta n time for this recurrence relation, right? Again, you can prove this, the correctness of this algorithm easily. Okay, you all know that how to calculate greatest common divisor, probably. Greatest common divisor can be calculated by using this Euclid's equation. This is recursive definition. We know that greatest common divisor of two integers m and n is equal to greatest common divisor of n and m mod n. Okay. And if n is divisor of m, or you can say n is equal to m as well, the greatest common divisor is n. This is the base case. This is the general case. And validity of this equation is, as I said, proved by Euclid. I'm not going to go into detail of proof, but you can prove this equation. And this one, of course, is a base case, right? And since this is recursive, it is easy to write this recursive method. N is divisible. Divisor of m means m mod n is 0. If that is the case, we know that we can return n. Actually, we do not need this part, since this performs that operation as well. But if m is smaller, we can reverse the parameters only. And to be able to calculate the value of this one, if this base case is not the case, then we can use this recursive definition. Right? I'm not going to go into detail, since the running time of this one is not easy to prove. Actually, after each iteration, we are not sure how small is this recursive call, but after two recursive calls, we make sure that the second parameter will reduce twice at least. So after second recursive call, we can make sure that, which is m mod n mod actually n mod n, the value of this one is smaller than or equal to n over 2, and we can use this, you can prove this, and you can use this to make sure that after second recursive call, the size is reduced to half, and after each two recursive calls, n to n over 2, n over 4, etc., after log n operations, we can make sure that log n recursive call, execute 2 log n recursive calls, we will reach to this initial base case at least. So because of that, the running time of this operation is logarithmic. So GCD calculation takes logarithmic time because of that. Okay.
Sir, can you say again why is it log n?
Now, at each recursive call, as you see, for this recursive call, m is greater than n, right? Clear, right?
Clear.
So m is changed to n. So the first parameter is smaller. So when you look at the problem size here and look at the problem size here, the first parameter is smaller. And second parameter is n, and m mod n here. M mod n is less than n, right? So it is again smaller. But how much smaller? As you see here, here we have n and make it n minus 1 and use this property to write this one, right? Okay.
Right, clear.
But how small is this true? I cannot say exactly how small is m mod n, right? M mod n could be 1, 2, 3, 4, or n minus 1, right? Any value is possible. We cannot make sure that it is very smaller. But after second iteration, if you perform one more iteration, means one more recursive call. So this will start executing. And then when we do one more recursive call, this will result in a GCD of m mod n and n mod n, right? Right? This will call this one, right? You can see that. If, of course, the base case is not the case. And when you look at the size of this one and this one, of course, since m is larger than n, the size of this one and this one, and it reduces. This one reduces, of course. But how much it reduces? And we can make sure that this value is smaller than n over 2. So the second parameter is reduces at least twice. Okay? So we can write the running time based on this n, en, and m is not very important in that case. Since how big is m doesn't matter, since as you see here, the value of n reduces twice. And n becomes n minus 2 after 2 recursive calls, right? And it becomes n over 4 after 2 recursive calls. And 2 more recursive calls, it will become n over 8. How many recursive calls are required until it reaches this one? When n is 1, this is always satisfied, right? It reaches to n equals to 1. It requires log n steps, and at each step 2 operations. So 2 log n recursive calls are necessary. And each recursive call, at each recursive call, what we perform is to perform just mode and check whether equal to 0 or not, check whether m is less than or constant time operation. So we perform 2 log n constant time operations. Then the overall running time will be theta log n. Actually, not theta log n. It is O log n since it is less than. It is a lot small. It can be a lot smaller. Okay. The running time of this is big O log n. If I said theta log n, it is wrong. It is big O log n. Since this is the worst case. Right? Is it clear now?
Sir, is there a way find the exact value?
No, it is not easy. No, not. So the running time, the best case running time is when m and n are equal or n divides m, right? And that is constant time operation. That's the best case. And the worst case is logarithmic time. And the general running time will be O log n. You cannot say exact running time in theta notation, since the running time depend on the relation between m and n. It doesn't depend on n only, but it depends on m and n and their relation. Not only size of n, but the relation of between m and n. N could be very large, but still divides m, and the problem is very simple. Is it clear?
Clear.
Okay. It is 11:29. Oh, zamanı bayağı bir aşmışız. Burada duracağım. Yarın devam edeceğiz arkadaşlar. Yarın recursion